Well, this is the second video on reduction and oxidation reactions. And we had the first cover, just reduction, mostly involving hydrogen being added to a structure through either use of catalytic hydrogenation, use of dissolving metal reduction, where we use a metal to give an electron, and either ammonia or HCl to give a proton. So dissolving metal reductions, catalytic hydrogenation, use of hydrides. Aluminum hydride was the more reactive form, and borohydride was a less reactive form, but both involved the addition of a hydrogen to a carbon as a hydride. So it had to be a polar double bond that we react with. We could not react with just alkenes. So if we had a reaction between a difunctional compound and aluminum hydride, the aluminum hydride would only react with the carbon in the carbonyl, not the carbon in the alkene. That was not the case with catalytic hydrogenation. Though there may be some selectivity towards one over the other, both can be reduced using catalytic hydrogenation. Some, I guess, discussion was given to the Wittig reaction, but not much, wherein instead of having a hydrogen added to the structure, in the Wittig reaction we take the oxygen in the carbonyl away and replace it with the R group from the phosphonium ylide. So that's still a reduction reaction because we're taking the oxygen away. And I didn't mention, but we do also have the Wolff-Kishner reduction. The Wolff-Kishner reduction, which is a complement to the Clemmensen reduction, metal with HCl, to reduce a carbonyl to a CH2 group. That was missed. Let's finish this video, and I almost want to apologize at the very beginning of this video just to say this, that we are not going to cover much mechanistically regarding oxidation reactions. We haven't done really that much with reduction. We're going to do even less with oxidation. There are certainly some oxidation reactions that are skipped, and there's much discussion of the mechanism that will be skipped in these oxidation reactions. What I'd just like to do is sort of present the reaction, the reagents that are needed, and the product that you get. So it's just sort of a summary of all the reagents, or typical reagents, that are seen in oxidation of alcohols, oxidation of alkenes and alkynes, and I guess some named oxidations wherein we take this is going to involve an alkene that we react with. And if we take the alkene and make let me just stop there. We're just going to have reactions of different functional groups with oxidative agents. So let's go ahead and look at our first oxidation reaction, which will be alcohols. We'll go to alkenes, alkynes, and kind of stay on alkenes and alkynes, or modifications thereof, with these last two. So the first one is oxidation of just primary and secondary alcohols. This cannot be done with tertiary alcohols. So in the first example here we have two hydrogens off the carbon that has the OH group off of it. That would be then a primary alcohol. Another way you can determine its primary is to circle the COH, and whatever number of carbon-carbon bonds you cut, that's determines whether it's primary, secondary, or tertiary. Here we see that we cut one carbon-carbon bond. So this would be a primary alcohol. Please just know that if you have potassium dichromate with sulfuric acid, you'll make chromic acid in solution between these two. And that chromic acid in water, and this is just required because the salt here, potassium dichromate, is soluble in water and we have to use it. If water is present, this will go to a full oxidation, wherein we don't stop at an aldehyde here shown below. We'll show you how you can do that, but it'll go to a full oxidation where we take both hydrogens off in the end, and we have a double bond, a carbonyl to an oxygen, and a single bond to an OH. We have a carboxylic acid. So that's what we get if we have a primary alcohol with potassium dichromate and acid in water. We get primary alcohols going to carboxylic acids. Second If we take the water away, so without water, if we have no water, well then we have to use a different chromium oxide because this is only soluble in water. So what they do is they make pyridinium chlorochromate. It has the same activity as the potassium dichromate, but they have something then that'll be soluble in something other than water. They call it PCC, pyridinium chlorochromate. And again, we're only using it because we need something that'll work in a solvent other than water. So we use our methylene chloride as a solvent, and there's no water present, then we can stop at just what's called an aldehyde, or you know this, where we take and just remove one of those protons, leave the other one behind, and have a CO double bond, a carbonyl, a final aldehyde, and we stop there because there's no water. If there had been water, it would go on and react to make the carboxylic acid. Lastly, the secondary alcohol. The secondary alcohol, again, it's secondary because when we circle the COH, we cut two carbon-carbon bonds. We can use PCC or potassium dichromate. It really is a waste of your money to use PCC because there's no way this ketone, in the presence of water, can go to a carboxylic acid. So we could use that. It's not that we couldn't, but it's not needed. We can use potassium dichromate, acid, and water, and we can end with a ketone. Something I didn't cover through all these reactions is to have oxidation using potassium dichromate or PCC, you must have two things within your alcohol. You must have an OH group, and off of the carbon, the alpha carbon, a hydrogen. Of course, we have that here. We have that here. We have that here, an H off the carbon, the alpha carbon. That's the one connected to the OH. We have to have both, the H connected to this carbon and the OH connected to this alpha carbon. But if you looked at a tertiary alcohol, where we have three R groups, there is no proton here. So that's why tertiary alcohols cannot undergo this same reaction. They don't have both the OH and that CH bond off the alpha carbon. Alright, well that's it. Let's keep on rolling along. We have alkenes we want to discuss next. The alkenes, you know, we can have a lot of addition reactions across this pi bond where this acts as the nucleophile. But we've covered in the videos on alkenes that we can run oxidation reactions wherein ozone, very reactive, we don't need a lot of it. This is in fact often made in solution, or with oxygen you can just make this in situ or whatever. We can run ozonolysis to get what's called an ozonide, lozonide, and you have a starting to break this pi bond, and even the sigma bond will start to break. And then we can do a workup with either oxidative agents or reductive agents. So what we have here is reductive agents. You can kind of tell because zinc in the full or the zero oxidation state is ready to give up electrons. And thiols we can take to sulfur oxides, so it's going to be ready to reduce something. So these are reductive workups in the ozonolysis reaction. If we have reductive workups, zinc with water or dialkyl sulfide, what you maintain in the reaction is these CH bonds. You cleave the CC double bond, and you put in place two oxygens for those carbons, but you maintain the hydrogens. So these are kept. If we would have run ozonolysis and oxidative conditions, this is hydrogen peroxide, we would lose those hydrogens. We'd still cleave and put the oxygens on, but on the other side, this carbon, we would have immediately carbonic acid. Just sort of highlighting these carbons here. We would immediately have carbonic acid with these carbons that have gained oxygens in place of the carbon-carbon double bond. But this carbon here is going to be, in the end, double bonded to an oxygen because this is carbonic acid. And carbonic acid will break down to CO2 and water. So you may see it as this in the book, but Often, more often, it's shown as carbon dioxide, because if you replace these H's with OH groups, as you should with oxidative workup of your ozonolysis, you'll have carbonic acid immediately, but it'll decompose to CO2 and water. You can run KMNO4 in place of, not the, first one with reductive workup, but KMNO4 in the presence of water, some heat. You can have the same products as shown in the ozonolysis with oxidative workup. So you can use KMNO4 in place of ozone, again with heat and water. All right, moving right along. So now we can look to alkynes. We've looked at alcohols, alkenes. Now let's look to alkynes, and then we'll finish with some just named reactions and we'll be done. Alkynes, we can run KMNO4 ozone. In the presence of water or slightly acidic water, we can get complete cleavage, and we don't have to worry about workup here. There's no oxidative and reductive workup like we saw with the last one, where we have to look at the second part to determine what happens to those CH bonds that were in the off the carbon in the multiple bond. That's only for alkenes. We don't have to worry about that with alkynes. You simply break that triple bond and put as many oxygens on that carbon as you possibly can. So we make 2 carboxylic acids. And in the presence of a terminal alkyne, a terminal meaning we have a end C carbon connected to a hydrogen. This is a terminal alkyne with ends at this carbon. We have just a hydrogen off of it. You're going to get CO2, not your carboxylic acid with this carbon here. You get your carbonic acid, but again that would break down to CO2. So we get the carboxylic acid with this carbon on the left, but we get carbon dioxide with this carbon on the right. Let's get to some named reactions. So epoxidation of alkenes, we can take the peroxy acids, and they have a structure wherein we have a carbon to a carbon oxygen in a carbonyl, and it looks almost like a carboxylic acid. So they call it an acid, but it's a peroxy acid. 2 oxygens off this carbon going to the right. So this is not carboxylic acid. It's much more reactive. It's a peroxy acid. These peroxy acids, in the end, insert one of their oxygens into this carbon-carbon bond to make an epoxide. So we just get a alkene going to an epoxide using peroxy acid. And this should not be a 1. We just work that up and we're done. Down below here, we're just showing a ring form of the alkene, making an epoxide. And of course we can make it on the top face and bottom face, but it doesn't matter because we only get one product here. Because we could have flipped it over if it had been on the dash. Of course we can just flip that over, the methyl groups being on the top. But of course if we flip this over, would be on the bottom and would superimpose on this. That's not always the case. Sometimes we'll have a racemic mixture instead of just a single compound formed from the starting alkene if this is an achiral reagent. So that's just epoxide, and we leave this in the carboxylic acid form after it's given up one of the oxygens. It's going to be this one here, but we'll look at that on the next slide. The methyl groups are the same. They have, of course, to be have to be on the same side of the ring because we've locked in the oxygen on the other side of the ring. Now I do give a little bit of the reaction mechanism for the Baeyer-Villiger oxidation. For this epoxidation of alkenes, we did not give a mechanism for that. But there is a little bit of discussion here on the Baeyer-Villiger oxidation. Epoxidation of alkenes, that's a little different than the Baeyer-Villiger oxidation. Baeyer-Villiger oxidation, we're working on a ketone or an aldehyde. And what we're going to do basically is insert the oxygen from the peroxy acid, the one in red, between the carbon here and the carbonyl, or the carbon here and the carbonyl. If it's a hydrogen, an aldehyde, it'll have the greatest propensity to react between that C and the H. So we say if it's an aldehyde, put it between the H and the C here. Make a carboxylic acid. If it's a tertiary, go before a secondary, and then if you don't have that, go to a primary, and then finally a primary alkyl, and then a methyl. So that's sort of the migratory aptitude for these Baeyer-Villiger oxidations, i.e. they set where the oxygen inserts. So if this carbon has a hydrogen off of it, you want to put in the end that oxygen between the hydrogen and the carbon. So the way this works is it's really just an attack on the carbon to make an addition product, and we transfer a proton over. So this is just the addition product, but there's just something that happens from that addition product of the peroxy acid where it's acted as the nucleophile and it's transferred its proton, the one that's here. But we then just have a strange relaxation from the tetrahedral state. We have a migration of that R group. If it's a hydrogen, take it. If it's a tertiary, take that. If it's secondary, take that if you don't have any of the others, and then on down the line. So you want to know this migratory aptitude. Hydrogens, and then tertiary carbons, secondary carbons, primary carbons, and then methyl groups. Oh, sorry, we maybe just want to say if you finish, you end up with either a carboxylic acid if it's a hydrogen, or of course an ester if it's one of these carbons, the tertiary, secondary, primary, or methyl. You end up with a ester. That R group is bonded to the carbonyl through that oxygen, and of course we get the carboxylic acid as a byproduct. Alright, just have a little bit more discussion on this. Probably going to go ahead and skip this slide. We can't talk about how this is more reactive as a nucleophile towards this carbon because it has less, I guess, pull from the carbonyl's oxygen, so it's a little more active. So I'm going to skip this slide and just say we could give some reasons for why this oxygen here, not the one next to the carbonyl, is more reactive. I want to end with two reactions that are sort of put back to back. We can have the hydroxylation of alkenes, the formation of vicinal diols. We can do two things. We can take that peroxy acid, epoxidation of alkenes, make a epoxide, and then just acid hydrolyze it so that we get a diol, a vicinal diol. Vicinal means off of adjoining carbons we have a diol, so off of adjoining carbons we have a diol. So these would be in an anti-addition form. Anti-addition, this is what we have here. Now this certainly can rotate, but the mechanism here involves an anti-addition. We protonate the oxygen and the water comes in from the other side. So this is just putting two reactions back to back that you've now learned, just epoxidation in this video, but way back when we looked at epoxides reacting with acids and water, we make vicinal diols. A complement to that, and using sort of a cyclic intermediate, is osmium tetraoxide, and the catalytic amounts or full amounts. Here we're showing it in a catalytic amount where we can use tert-butyl peroxide as a source to regenerate the catalyst. But either way, the active agent here is osmium tetraoxide. It can bridge these two carbons and in the end leave us with two hydroxy groups across from each other, a syn addition, not an anti-addition like we have down here of two OH groups, a syn addition. So either way, formation of vicinal diols through hydroxylation of alkenes using osmium tetraoxide or using peroxy acid in an acid-water workup. And we can take those diols. Now this, if they were across from each other, would have to have been made using osmium tetraoxide. We can take periodic acid now and cleave completely the carbon-carbon bond in the vicinal diol. We can cleave this carbon-carbon bond in the vicinal diol. It is actually a bridge, again, cyclic intermediate using the iodine and these oxygens. We can get a bridging. In the end, we break this carbon-carbon bond, and in place of it, we have two carbonyls. So these oxygens are going to be double bonded to the carbons they're off of. So we can just sort of asterisk this one, cut this in half, and say I take the H away and have that oxygen bonded, double bonded to the carbon that it was previously single bonded to. So we can take again that oxygen here, double bond it to the carbon that it's bonded to through just a single bond. This is just oxidative cleavage of vicinal diols using periodic acid. You do not need to worry too much about these side reagents or side products that you get, but you do need to know what you get as a product. If you take a diol, periodic acid, and have a reaction, you get two, ketones if these would have been R groups off of this carbon, but there are hydrogens that are on the dash, so we have two aldehydes. We can do this with a lot of different diols. It is important to remember that they have to be off of adjoining carbons for this reaction to occur, and they often work best if they're cis to each other. It's fastest if these groups, of course, are cis to each other, because then they can make that bridging structure with the iodine in the periodic acid. So it's best if they're cis to each other. Well, that's it. Says something about it used as an analytical tool, but we do need to know this reaction. So we've kind of going back all the way to the beginning. Okay, if I can find my beginning. There we go. We've looked at oxidation of alkenes, alkynes, alcohols. We've looked at the Baeyer-Villiger oxidation, where we can take, this is not the alkene, this is the carbonyl that we can insert. We can insert the oxygen between one of these two R groups, depending upon whether it's tertiary, secondary, primary methyl, or if it's a hydrogen, we would insert that oxygen in between the R group and the carbonyl, the hydrogen and the carbonyl. That's the Baeyer-Villiger oxidation. And then we looked at formation of diols using osmium tetraoxide or peroxy acids with acid-water workup, and then the cleavage of the diol using periodic acid. That's it. It's not a lot of discussion of the mechanism. I hope that kind of hurts to not see those mechanistic details. But I just wanted to summarize what your products are and what those, what the reagents have to be to get to those products, just so you can maybe recognize those, in some sort of assessment or whatever. Just to know the associations of reagents with products. Bye-bye.